All right, today we are talking about potential energy. And so what we're going to do is say that potential energy, just like you guys said in the 8th grade, is stored energy. We're going to do work against something, and it's going to hold all of our work as stored energy to come out later. So we're going to look at spring potential energy, and we're going to look at gravitational potential energy. But it's a pretty, overall, pretty simple concept. Okay, so let's jump into it. Now, to do that, we have to talk about a new kind of force, or a new way to distinguish between forces, conservative and non-conservative force. Conservative force, right, our horrible definition in most books, is the work done by a conservative force does not depend on the path taken. Here's the deal. Gravity is a conservative force. If I lift an object to here, the work that gravity does is the same as, let me go straight up, is if I lifted that object way up here and brought it right back down. The work to get the object to go straight up to that point and the work to move it all the way around here and still get me to the same height is the same. It doesn't depend on how I got there. A better functional definition is that work done against a conservative force can be stored. I can store that work up. Non-conservative force is the opposite on both of those definitions. One, the work done depends on the path. Imagine pushing an object from here to here against friction. If I go straight there, friction does work that is the force of friction times the length of this path. If, however, I go all around and I push it over here and I bring it back and I end up here, well, the work done by friction that time is going to be a lot longer because I was pushing it a lot farther. So it depends on the path taken. Also, a non-conservative force cannot store work at all. It's gone. If I do work against friction, I lose it. If I do work against gravity, that thing's going to fall back down. I get it back. Now, as we're talking about these conservative and non-conservative forces, we're not going to have to do a lot of distinguishing between conservative and non-conservative. Okay? For our conservative forces, we have two that we're really going to look at. One is gravity. The other is elastic force. This would be like from a spring or rubber band. Then we have a non-conservative force. The only one that we're really going to talk about here is friction. Those are our conservative or our non-conservative forces. So, potential energy. Potential energy has everything to do with conservative forces. So for our book definition, potential energy is the work done against a conservative force. That's great. So let's look at a very simple example. Let's say we have a 5 kilogram mass. We're going to lift that up a distance of 10 meters. Now, we know the weight, the force of gravity acting on that is 50 newtons. And I'm going to go ahead and say that I'm going to pull up on that thing with a force of 60 newtons. That's me. So we have the work that I do, my work. Well, my work is 60 newtons times 10 meters, or 600 joules. And we have the work of gravity. Well, that's going to be the 50 newtons times 10 meters, but they're in the opposite direction, so it's negative 500 joules. Now, those are the only two forces we have, so we also have a network. Add those two together. My network is 100 joules. So, looking at everything that happened here, I did 600 joules worth of work. Now, 500 joules was against gravity. "100 joules, which is my network, became the kinetic energy of the object." So, I did 500 joules worth of work against gravity. That didn't make me go any faster. That 500 joules worth of work against gravity is what lifted the object up. This is what has now become our potential energy. It's the work that I did against gravity in lifting the object up. So this object now has 500 joules worth of energy. But I don't really like this definition. Okay. Work done against a conservative force. It's not how I would say it. So let's erase it. All of this. Leave that up there. We're going to use it. Now, what I'd like to say is that potential energy, that stored energy, is the opposite of the work done. By a conservative force. The opposite of that. So, same situation. Lift my 5 kilogram mass up by 10 meters. The work done by gravity here, we said, was negative 500, which was negative weight, mg, times my height. Well, my potential energy is the opposite of that. Gravitational potential energy is opposite of the work done by gravity. So in this case, it's going to be 500 joules. So if the work done by gravity is negative mgh, our general thing for potential gravitational energy, U, is positive mgh. Now, just a couple notes on potential energy. We use U when we talk about potential energy. I don't know why, but every time you see a U, that means potential energy. And because it's energy, it's measured in joules. So, what we're going to stick with for potential energy is the opposite of the work done by a conservative force. Gravity does negative 500 joules. My potential energy is 500 joules. Now, elastic force is new to us. We haven't talked about springs yet at all. So, imagine we have this spring, and initially my mass is sitting right here at this x equals 0 position. So I am going to come along and pull with the force F and stretch that out. And the spring is going to pull backwards against me. Now that force works this way. The farther and farther and farther I stretch it, the more and more and more my force gets. So if we were to look at a graph of my force versus the displacement of the spring, this says that the farther and farther and farther we stretch it, the more and more and more I have to pull. Because my force is in the same direction as the displacement, all of that stuff's positive. So, looking at this graph, I know the area of the force times the displacement graph is the work done. So my work that I'm doing against the spring is 1/2 times x times the force, which is 1/2 times x times kx, which is what gives me the 1/2 kx squared. All of my work is being done against the spring. Likewise, we could look at the force of the spring versus the displacement. Now that's going to be negative because the spring is pulling against the displacement. I move this way, the spring pulls back. But in the same way, that area is going to be the work. Now, the work done there by the spring is going to be negative 1/2 kx squared. So the potential energy stored in the spring is going to be 1/2 kx squared, and it's positive because, again, potential energy is the opposite of the work done by, in this case, a spring. Now, this guy, K, it goes by a lot of different names. Spring constant or force constant. All that does is tell me how easy it is to move the spring. A very stiff spring, like a car spring, has a very high spring constant. A very loose spring, like a slinky, I guess, has a very low spring constant. Just how hard it is to stretch the spring in. Now, gravitational energy. We've already kind of talked about this. I have an object of mass m, and I move it up a height h. Potential energy is going to be the opposite of the work done by gravity. Well, the work done by gravity is negative mgh. So my potential energy is going to be mgh. So for gravitational potential energy, if I apply a force F this way, and the box goes up a height of h, it does not matter what I do here. Okay? mg is pulling down, it's being displaced a distance of h that way. The gravitational potential energy is still going to be mgh. My work may be something different, but the gravitational potential energy that happens there is m times g times h.